Couple of things, pretty much where we left off, it was like right at the end where we had the Ladybug analysis. We had all of our shapes that could then all move. And there's a couple of things that pretty much we had to do was just pair up our output data from Ladybug with our geometry and our geometry transform. Not now, I don't need this, I've already got it. Oh, I'm just waiting for it to work. So just very quickly going to draw out a couple of curves here, and we'll get one more, maybe going like this. Oops. I guess we'll just take you over here for now, and then I'll grab one more maybe that's going up like this. This isn't important. Yep.
When I moved to Rhino 7, I forgot to reinstall whatever the Weaver bird,
Okay.
whatever that was tied into. Would you remind me what that was, through what the Weaver bird nodes were downloaded through for Grasshopper?
So I think there's a food for Rhino site of how to get Weaverbird, but it will lead you to a specific website that is Weaverbird for Grasshopper in some ways. Okay, so now I'm going to grab this one. Maybe this will be our middle. This will be our top. I've got to set these in. Oops. Okay, so now we get our crazy hexagons here, and this is pretty much right where we left off. There is one thing that I do want to revisit in a smarter way than using the dual graph to get non-whole hexagons. And the way to do that is to explode all of your hexagon shapes and then count the number of sides. If it has less than 6 sides, it's not a full hexagon. So then you can call that out, and we'll show how to do that rather than using the dual graph here, which I think is kind of a cool way. This is kind of the first section that I wanted to work on because it does make it a little bit different. So if we look back at our, these are our triangle B patterns, so they're not even actual hexagon patterns. Oh yeah, because we're using the dual graph. So what we can do is come into Lunchbox, and if we did want to use our hexagonal cells and start from there, we'll bring that in, we'll bring our U, we'll bring in our V. I think I wanted to maybe switch those. Hey, that works. I like that. It's really complicated and looks kind of cool too. But the issue, again, was like these edges. So if we just count the number of edges in each cell, and if it's less than 6, then we just get rid of it. And that's a kind of a cleaner, more efficient way to do it. The dual graph is really cool though. I think I like to see both of the geometries kind of working together, but because we're not leveraging that data, that information, there's no sense in us kind of working through that. And I did want to just be able to show this. So we take our cells and then we explode, and it's explode curve. And then we can look, and if we open up, if we go to param viewer, we look at our segments, we can see the first one has 4, we have 5, 5, 5, then we get into our 6s. So we're just going to get rid of anything that doesn't have a 6. And the way to do that is if we come into our sets, so this is like data trees part 10. If we come into our trees, we can go to prune tree right here. And we're going to bring in our segments as our tree. And the minimum is the remove branches with fewer than n0 items. We can see our n right up here. So if it has fewer than 6, we're going to remove those. And then we're going to join those curves. See, we only have our whole hexagons, which is kind of a clever way to do it. We could also invert this. So if we wanted just our edges to handle those separately, maybe they get a different geometry Maybe it's important. Maybe they're important to have. You could set your max to be like 5 and no minimum, and it'll give you the opposites. So I'll just show you that for really quick. Again, I am just assuming that your design will be different and you might want this behavior. And then we can just disconnect this. And so now I just have my edges. So kind of a cool little trick there. It doesn't require anything other than out of the box grasshopper components to kind of get to the same place, almost the same place that we were here. So I'm just going to kind of leave this as its own group up here for now. It's not going to make or break what we're going to do next. And I'm going to hide it because we're gonna use it just a little bit later, but not right now. We're going to make some kind of cool stars a little bit, I think, what might be fun. Play with some more kind of list item stuff. So then what we have here is, if we recall, we have all of our surfaces, all of those kind of 6 parts of our surfaces, all being linked in. So each hexagon then has all 6 of its pie pieces in its own kind of data list here, is data tree. And then we went and we decided we were going to kind of chunk up this data, but we don't have to do that. And I'll show you why. So I can take this and delete it. And what we want to do is we want to change the angle of all of this. So actually, rather than doing it, I mean, it was good for the sake of example to do it discretely for each one of these up here. But in terms of actually manipulating our geometry, we now have everything kind of built into this node here. So we can actually extract out all of the information we want just from this node here. I say deconstruct brep, and I bring this in. So now what it's going to do, we'll look at our data structure, but now I have the same list of faces, and that same, we can see it does get kind of crazy. There's a couple of zeros in there from our other bits of stuff, but our data tree from that and our data tree from this are identical, which is really important, again, because what we were essentially getting is our axes and our geometry we were trying to rotate had different paths. And then that was causing like the mayhem. So now we can take our faces as our rotation, and then our edges are the ones we're actually going to list as the index. We can delete this because that was our old method that didn't work. And now we still have our original rotate piece that's changing these, right? So we can still flex these accordingly. But what we want to do is we want to replace this with the output from Ladybug. One thing I want to do too is that I don't like the default colors of Ladybug, and I'm sorry, Mustafa, because these are good colors. They're not bad, but I got hooked on the colors from a really old legacy experiment from Autodesk that was called, something, but it was before Dynamo, and it was like environmental sim for Revit in like this Dynamo canvas. This is like way before Green Building Studio or anything. They had some cool stuff. Autodesk has killed as many cool things as it's made in the last little bit, maybe. At least that's the way it feels like. They got rid of point clouds in Revit and then made it recap. Used to be able to do all of that directly within Revit. Same thing with the environmental analysis. All of that was like by default in Revit and worked really well with Revit. And then they pulled it out, and then now it's its own software. I guess that's an easy way, is you can kind of crowdsource that. So anyway, what we want to do is we want to look at, I'm just going to open up a panel here, and we want to look at our results If we look at them, we have this kind of long, 1812. So we want to be able to translate 1812 into a rotation for our flappers. I come up with a better name than that. But so if we look at this as just data, I'm going to make a data container. We could also put this in as a number, but just a data container is kind of a general catch-all. Again, I like to kind of put that at the forefront of like any group that I'm building to keep things a little more clean. And we're going to remap all of these numbers into a value in between like 0 and 1 pi, which is 180 degrees. We can change those into degrees if we wanted to do like 0 and 180. We'll play around with that. And the way to get there is to go to totally having a brain fart there. We go to our math tab, and under the domain, we have this remap numbers tool, which is really, really useful. So this will allow us to take all of these values that are within this crazy domain of however many thousands of kilowatt hours, or we're talking about radians here, so it's a little different. But I'm going to take all of that, and we're going to find its corresponding number within a new bounds or a new range. So the way to do that, if we come in here, there's a way to get bounds, and this will find our minimum and our maximum within that data. So we have 331.00009, or this extra 0 there, and then 1829.6 and some change is our high end. So we want to take all of those numbers then within that bounds and then map them into a new bounds that we create. So our values are going to be the data that we're actually using. The source domain is what we've got from this bounds, and now we can make our new target domain. We can make that whatever we want. But in this case, we're going to translate it to radians or a rotation. So I'll need to construct a new domain. So up under the domain tab or domain section of the math tab, we can go to construct domain. I'm going to bring that into my target. And my domain start, I'm going to say is 0. And my domain end, again, because after 180 degrees, like that geometry is just going to like wrap around itself, which we could do, which could be fun, but we don't need to. So that would be 1 pi. So I'm going to say 1.00, just so we have a couple more decimal places to play with. And now the new map values, as we can see, are all coming out between 0 and 1. And so then we can grab up a pi value, bring our map values in there, and then now we actually can get rid of this upper one, because now we have a new value of pi. So if I take this, bring it over so I can kind of see what's going on, and I can grab a couple of these just to clean things up a bit. And I bring this in for my angle. It's going to think and probably crash, sorry. Oh, because I didn't graft it, right? So now I have I'm applying that rotation 10,080 times times 10,080 times, right? Because each one of them are in their own container, so it's going to apply each one of those rotations to each one of the containers. So if I click on this, we'll see some probably madness. Oh, sorry, little graphics card. I shouldn't have clicked on that. We'll get there. maybe. This might actually be the thing that crashes it. Essentially, I should have checked those data sets before I brought that in to make sure everything was matching up. Can I escape? Nope. Okay, that's okay. It'll think. Hopefully this graphics card can keep up. Oh, yep. You can see it's just a solid green because there's 1,000 of them. So if I just graph this, you can see now it runs really smooth and super fast, which is what we should have done in the beginning. So again, if we're looking at our data structure, when it's flat, and actually I can show that here. So grab another param viewer. I'm going to grab a couple of them. So here we have just one branch, and here we have 1,032 branches. And so the issue was that when there's just one branch, it's applying that one branch to each branch until it runs out of branches, and then it'll just keep applying them. If we remember from like the first day when we were going over data sets, when it was like connecting and the list wasn't long enough, it just takes that last one and just connects the rest of them to it. So it'll do a similar thing, but in this case it's doing a rotation. So we're giving it 1,032 rotation angles, and it's applying, because it only has one branch, to every branch within that list. It's not what we want. So if I bring in a graph, I'm going to graph this tree, I bring that over, and I look at what that is. Now I have 132 branches with only one item in it, which is what we want. So I can actually, I can hit lock. I don't know, this is another nice trick. If you right click on the canvas, there's an ability to lock this solver. So it won't compute anything right now. So I can actually move this stuff around without having it totally explode on me. So I'm actually going to use this graph over here, just so it's kind of written out a little bit more clearly. And then I can say unlock, and it'll rerun that for me. But the cool part is now, if I hide this stuff, is that what I'm getting is a rotation based on the amount of radiation in each one of these. And I can kind of flex that a little bit more. So the ones that are blue are like pretty much closed. So we can see kind of over in this edge. And the ones that are orange are pretty much completely open. I think. Are you getting something different?
I think mine's different.
Okay. Can I see?
Yeah. So like, trying to find one.
One thing that I would say, so we said 2 pi was the maximum. I'd actually bring that down to, or 1 pi was the maximum. I'd bring that down to 0.5 so that the maximum is going to be perpendicular to that surface. And that'll help a little bit because at 1 pi it can essentially open, and it can open itself all the way up, but it'll close its neighbors, and then its neighbors are doing that to it. So I just dragged mine down to 0.5 right now. And then that helps me get a little bit better visual here too. I can see the ones that are kind of poking out and the ones that are a little bit closed, which is kind of fun. Is everyone here now?
No, I think it is. It just looked weird when they were like.
When they they're all kind of jumbled together.
Mm-hmm.
And that's one of the things I said I didn't like about our logic here for this, but it's kind of a proof of concept. So what we could do, and we'll do this actually pretty quick here, I'm just going to say file, save document as, I'll call this 02. we can either do the sunshade one or we can do like the aperture one. Which one sounds most fun?
What was the sunshade one again?
Though we're gonna change how far out our sunshades project from the surface based on the value we get from Ladybug.
I feel like I would use that one more, but the other
Cool,
one sounds
cool.
more fun.
All right, we'll see if we can't get to both. The other one should be pretty quick. So I'm gonna come back up here. I'm gonna grab a surface. I'm gonna grab this surface in particular. I can actually hide all of this. I'm not going to be using any of this. And I'm gonna be copying some of that down later. But so now I've kind of got my new area here. I'm just gonna hide everything except for that new surface, including the Ladybug stuff. So we can start here. We're going to divide this into quads this time, and for the reason of our sunshade, well, I guess it doesn't matter if you used quads or not. It's just a different way of handling that logic. So there's, again, you're the master of your own kind of script here. So you could use the center points of the pieces. You could use, there's a million and one ways to kind of go about this, but just for fun and a refresher, we're gonna go back to like a square one. So remember how to do that. We use ISO trim. This is the out of the box method. So we're gonna grab this surface, and for our domain, we're gonna divide the original domain. So we use a divide domain squared. Divides a two-dimensional domain into equal segments. So we're gonna grab our surface as the domain, and we're gonna add in our own U and V count. And I'm just typing the numbers in to give me a quick number slider here after I double click on the canvas. And then I bring that into my domain. I can hide my original surface, and I can see now I'm getting like a divided shape. So now what I want to do is I want to grab like the top edges of each of these curves and project them outwards so that they make a sunshade. And I'm just going to use, for this example, I'm just going to use like the y-axis, but we could use something like the normal or whatever, and we could make it kind of splay and twist and curve and do all types of stuff. But just for the example here, that y-axis is going to be our kind of bread and butter. So I'm going to do the same thing. I'm going to deconstruct this now with a deconstruct brep. This will give me my faces and my edges. And for my edges, I'm going to list item and find the top one. And we can see here, so I have one of the side edges, which is my 0 index. And that's kind of cool. We could use vertical louvers instead of horizontal ones. Like, you know, everyone argues that vertical louvers don't do that much, but I actually had a project that was just about proving that to a client because they wouldn't believe us. And so I ran a whole bunch of simulations, like side by side. And it turned out the vertical louvers on a west-facing facade actually helped the building more for the time period it was being used. So they're like, well, at sunset, they're not going to block anything, but everyone was already home, so there's like 0 occupancy of the building. So it's like, you're right, but, so let's use vertical for now. That'll be fun. So we'll extrude all of these kind of out from the Y in a solid direction. And we can flip this pretty easy just by changing our index. So we can, maybe we'll do both. I don't know. We'll have some fun with it. And so now I'm actually going to copy our Ladybug stuff, except for I'm not going to bring in this surface. I'm going to bring in a different surface. So pretty much all the way from, all of this stuff is just reorganizing the data that we're getting out of Ladybug, which we're going to want to do again. But this is really all that we're using to generate the Ladybug stuff. So I can grab this. It'll take a little while to copy because it's rerunning everything. And for my new surface, I can grab all of these faces, or I can just grab this surface here. And I have to bring in a surface. I like to keep everything in kind of neat little containers here to help me manage them around. And this will be my geometry. And then I can show this, and I can hide these. And so now we can see I've got kind of my quads acting as this. Oop, got one more here. So now here's my quads. One fun thing I'm going to do is change the colors of these. So if I go into, it's asking for legend par or legend parameters. Oh, there's one more fun thing about Ladybug that I learned, is that if we look at the names of each one of these, if you see a dash, if it starts off with an underscore, it's a required input. If there's an underscore after it, it's not required. And if there's one in between both of them, it's optional. So that kind of an aha moment for me, because I was like, man, they kind of name these like, you know, sporadically, and I figured out that it's not an accident. So if you're ever opening up one of the Ladybug or Honeybee nodes and there's like 50 different inputs, which with some of them there's like 50 outputs, but if there's this many inputs, you can kind of go through and quickly visualize which ones you need right away. But so for this, I'm going to change the legend parameters. So I'm going to go into legend parameters, Ladybug legend parameters, or LB. Bring this into my legend parameters here. It's not going to change anything because it was left at its defaults. But what I want to change are the colors. The colors are the main thing that I want to change. And there used to be one that had a couple kind of pre-built in there. That might still exist if I go to colors. No, I don't see it. So I'm going to make a gradient node. And I'm going to change these colors now. So if I double click into this, I can kind of move around each of these values and edit this a little bit more. And I'm going to add one. And drag these out. So for this one, I'm going to make red. No, this one's going to be yellow. You're going to be a yellow. Pure bright yellow. Yeah, we'll say okay. The middle one I'm going to make red, pure deep red, and then the far one I'm going to make a deep blue. And these are the original, the OG colors. So I'm going to say okay. And then essentially what it's asking for here, we're going to kind of fake it out because we don't have the upper or lower limits of what the values we're trying to analyze are. But we can figure out the parameters that we want to evaluate these at. So if I just type in a series, and for my step, I'm going to make this a 0.1. So now I've kind of divided all of this up into a bunch of little chunks so that I can then map those onto my legend. I can bring this then into my colors, and I get something that I like to see. I like this a little bit more. It seems a little more pleasing to me. I don't know why. Maybe it's just the nostalgia. But I did want to show everyone, so there's another way we could do this. We could say gradient. This one, it would be really useful if I was doing like shadow studies. Right? So a whole bunch of different ways to analyze this, and then you could even match these colors to be like the colors of your final boards, or, you know, fun. You could do some fun stuff with it, right? And this is all, again, too, about, like, sometimes someone looking at this isn't going to go through and be like, I see that quadrant 7 has 0% shadow. It's mostly like they'll get it intuitively based on how you present, and that can almost be more powerful than the actual information to someone who's not doing the work. For us, we want to know each one of those like specific values, but for the final kind of eye candy piece, we can explain that without words, but like win the commission. Anyway, just kind of two ways to go about that. Maybe I'll leave it colorful for now.
Can you bake the color into Rhino, or does it have to be in Grasshopper?
You can bake that into it, and it is this mesh.
Okay.
And so if you bake that mesh, I believe the colors will come with it. If not, there is another way to do it. I haven't looked at that in a while.
Okay, that's fine. I'll play around.
Let me see. Let's just try it out. We have time. And take this mesh. What layer am I on default? We'll bake it. And then we'll turn all this off. And then we'll come in here to shaded, rendered. Yep. So it does. It bakes all of those meshes then have their own inherent color. And that actually looks better than the Ladybug version, which is kind of fun. And I think each one of these are their own. Nope, it's come a long way. You used to have to use a specific plugin to get the mesh colors. You'd map all of the colors to the specific meshes before you bake them. But then you'd get each one of these as their own mesh. Then you'd have to go and rejoin those. Now Ladybug comes with all of that included, which is fun. Okay, so back to this. Did a little sidetrack looking at kind of colors and stuff, which is, I think, kind of fun. So now we're going to grab, if we come back here, we're getting one of our edges of our quads. And because if we look in here, we have 648 values for our quad edges. And if we look at our results, we have, well, I'm going to use a param viewer to see that. We have 648 values. And because we haven't grafted or done anything crazy with our surface, everything is just in flat kind of data sets. So it should match up one-to-one pretty easy for us. But we do have to, we are going to do a couple more things to kind of modify this. One is I'm going to get probably the centers of each one of these. So I can do point on line, or point on curve, excuse me. And we'll bring that in. So this will get me the midpoint of each one of our lines. And then I'm going to move those. I'm going to move this geometry. I'm going to move it in the Y direction as we discussed, so unit Y. And I'm going to give it an amplitude. Well, I guess I don't have to do that. I can just use the factor, so I don't have to change the amplitude. So now I have all of these moving, and I'm going to want this to be a negative because I'm going to move it towards me in camera because that's the way that that's like the outside of my surface for this example. I just made that up, so that's the way I want it to go. So I'm just going to use this as a negative to show again that I can kind of move those around. So now it's only moved by 1. But if we come back up here and we grab our logic of how we remapped that data, I can then bring that down, maybe, over here, bring my results in, my new results, and then for my domain end, I'm actually going to make this like, my max is going to be maybe like 50 feet or something. Because I'm not doing a rotation, I'm doing an extrusion. So I want my extrusion to go a little bit further. And I can bring that over. If I look at this, I don't even have to flatten it anymore, and I don't have to multiply it by pi. I can just literally bring it up over into the factor of my unit y. So I don't need you, and I don't need you, and I'm just going to take this stuff and drag it over so I can see a little bit better. And now, well, I guess I can turn all of that off. And now I can crank this up because now my maximum is 0.5, so it's really hard to see. If I crank this up, oh, I do have a mismatched data set. We can see it's moving it like 600 times in here. So those are all points. So right up in here somehow, where did that graph come from? Oh, from my list item. So if I flatten those, it just gives me 1 and 1. So now what I'm going to do is take that original point and then the move point, make a line from my start, my end there. So now you can see I'm starting to get what these sunshades might look like. And then I don't have these grouped at all, so I'm going to want to partition all of these lines according to how many my U divisions, which came from that original surface, from that ISO trim. So if I come in here to my sets, I can come into list. There's one called partition list into sublists. So I'm going to bring all my lines in. And then for the size, I'm actually going to come way back here and grab my V count and slowly travel all the way across the canvas here, or I'll just use the claw method. Bring that into the size. And now I'm getting I'm getting 11 branches with 57 items within that, which again corresponds directly to our divisions of that original surface. So now I can loft these together and get an error because we're starting at 0. So one of these lines is as a 0 length, and lofting doesn't like that. So if I change this to like here, and then we'll go like 0.001 will work. And you can see now it's happy. All it needed was just a non-zero number. The next thing I'm going to do is take these lofts and, well, I guess I could kind of just leave them as is. I might give them a custom material. So say custom preview, and then the material, I'm going to go color or swatch. Color swatch material. We'll make them like black. So we can see them a little better. I can hide this stuff and this stuff. And we can see we're getting like a dynamic sunshades. And we could give those a thickness, we could add tiebacks, we could do like all types of stuff, again, but hopefully we've gone over enough of like list logic. Like essentially you could take the class where we went over the space frame, and you could like apply the space frame logic to give you like a structure underneath that. Another thing I've seen people do is they build like an armature on the outside. So like this could be the inner row of your space frame, and then your space frame thickness could be dependent on light, which isn't structurally sound but could look interesting. There's kind of a million and one places you could go with it, but hopefully this is kind of a fun, cool looking, well, it's not cool looking. It's, for the example's sake, it's interesting in the sake of it being an example. It's, I just made all of this up. It's arbitrary. So it's, hopefully whatever you do is a lot cooler.